So, we talked about p-n junctions and how diffusion takes place in semiconductor p-n junction, and we suppose this is your p-n junction that we represent in this fashion. This is p side, this is n side. You have depletion region, and then you have lot many electrons here and lot many holes here, and we discussed how these holes and these electrons are distributed in different quantum states of different energies. Okay. The band looks like this one. Suppose you have this Fermi function. We introduced the concept Fermi energy EF, and then for p side this Fermi energy is close to the valence band edge. The conduction band edge is here. So, these quantum states correspond to all those conduction band energies, and these quantum states are in valence band. So, this is our p side, whereas for n side, it is close to the conduction band. So, this EC is here, and then all these quantum states are here. All these quantum states are here. These are conduction band, and EV, that valence band, will go somewhere here, and you will have this valence band quantum states. Then it bends and joins with this EC. This bends and joins with this EV, and so on. Now, how many electrons are here in these quantum states? How many are in these quantum states? How many are in these quantum states? And so on. So, for that, once again you have to go to this Fermi energy. This Fermi energy that tells you you have a Fermi function, this Fe, which is 1 over e power e minus Ef over kT and plus 1. So, this gives me the probability. This at E equal to Ef, the probability is half. So, if you are right here, there is no quantum state here, but if there is a quantum state here, the probability would be half. And then for example here, or for example here, or for example here, you can ask what is the probability that there is an electron here. We discussed all those things, and we found that in n side you will have large number of electrons. You will have large number of electrons, and then as you go up in the energy, that number of electrons per unit energy will decrease, and so on. And most of the time, if you are quite away from this EF, this decrease is exponential. The density of state also comes into picture to decide this number of electrons here, that distribution. And right at the bottom, you remember, right at the bottom the density of states is 0, and then the density of state increases. So, it maximizes not at the bottom, but a little bit above. But we are not concerned with this, we are mostly concerned with this. So, here the concentration decreases exponentially as you go up in energy. Similar is the story for p side. Here you have holes. So, you look for the probability of not occupying this particular quantum state, 1 minus Fe. So, that gives you probability of a hole being there in valence band. And then once again you have large number of holes here, and then as you go down in energy, this will exponentially decrease, and these quantum states will have lesser and lesser number of holes. So, all these things we discussed. Then if there is a concentration gradient, we have diffusion, but which electrons take part in diffusion? Here I cannot say which electrons take part in diffusion, but here we can, because you have this barrier. because of this energy barrier. You have this energy barrier here. You have this much of energy barrier. And so these electrons cannot diffuse. If these electrons try to go from n side to p side, crossing this depletion region, there are no quantum states here. Only these electrons which are above this level, only these electrons which are in these quantum states, they will be able to reach here. At these energies, you have quantum state here on this side, and therefore they can only reach here. The more energetic one can reach here. Similarly is the case for these p side holes. If these holes, these majority carriers, if they want to go to n side, then these holes cannot go here. You don't have any quantum state. Only the holes which are here in these ones, only these can migrate here. Okay, only these electrons can migrate here. So these are the electrons and these are the holes. But such migration will take place because of the concentration gradients. The electrons will try to diffuse here, and then the one which are having sufficient energy, they will go, and therefore you will have a current. This is the current because of this electron diffusion. You can call it I diffusion because of electrons, and the direction will be opposite to the direction of electron movement. And here, because of this hole going this side, you again have a diffusion current. You can call it I diffusion because of this holes, and the direction is once again the same, and so you have I diffusion, which is equal to I diffusion because of electron plus I diffusion because of hole. So you have a current from p side to n side. In this diagram, you have a current in this direction, I diffusion. But then we have not connected this p-n junction to any circuit, no cell, no battery, nothing. It is just lying there on the table. So how can there be a current through this junction, through this system, without charges being accumulating at some places? This is all steady state that we are talking of, thermal equilibrium we are talking of. All this inbuilt potential difference and this energy difference and barriers, all after everything is settled. You cannot keep on sending this current without connecting any battery or something. So what is the other mechanism? We have talked of majority carriers. We have not talked of minority carriers. You also have minority carriers. And how those minority carrier comes? If you have electrons here, if you have holes here, from where they are coming? The majority carriers come because we have doped the system with impurities, and minority carrier comes because of the thermal energies. Because of the thermal energies, whole electron pairs are continuously created and continuously destroyed also. Recombination also takes place through some mechanism. So you have recombinations and you have thermal generation. Those things keep going in any part of this semiconductor material, and these minority carriers are essentially coming from that, and that process takes place throughout. So you have here also in the depletion region also EH pairs are created and also EH pairs are destroyed. But then you have electric field here. Okay, in this picture, the electric field is in direction n to p, because all these negative charges will accumulate here. You will have negative charges. Those ions, those impurity ions being exposed because the hole has migrated or it has recombined. So those ions are exposed. You have positive charges here. So you have electric field. So as soon as this EH pair is created, this electric field will exert force on this newly created electron here, and that electron will be pushed in this side and the holes will be pushed in this side. So that mechanism also you can understand from here. If there are minority carriers in the depletion region or close to the depletion region, somewhere here, let us say these are generated, suppose it is generated here, then it diffuses into the depletion layer and then this electric field takes over. So if you think of those minority carriers, this is p side here, so lot of holes are here and some electrons are there, and where are they sitting? These electrons are sitting in the conduction band, right? These are the minority carriers. And if these minority carriers, because of this electric field, these electrons, they will tend to go towards that n side, so they will tend to go in this direction. These electrons, they would like to go in this direction, and there is no barrier. There is no barrier. They can very easily go. This electron can go, this electron can go, this electron can go, everything can go. And similar is the story for this n side. Here the electrons are in majority and holes are in minority, and these holes are here in the valence band. If they want to go towards this p side, no one stops them, no one says that no, because you have all quantum states available. So this barrier is not a barrier, rather it is something which helps. If this is the electric field which pulls, here the electric field which pulls it on the other side. So you will have, because of this minority carriers, you will have a current. And what is the direction of that current? The electric field is taking these electrons from p side to n side, and therefore the direction of current will be in this picture from right to left. So because of this, you have a current which we call drift current. Anything that is in the influence of this electric field, that is known as drift. So it is drift, and the direction is in this direction, right to left. And here also the holes are going, these minority carriers, these holes are going from right to left, and the current is also from right to left. So you will have I drift. So this I drift is because of the electrons, and this I drift is because of holes, and that is also going right to left because holes are positively charged. So holes are going from this side to that side, so that is also the current direction. So you add these two and you have drift current, I drift, which is I drift because of electron plus I drift because of holes, and that is in the direction of n side to p side. Diffusion was in the direction p side to n side, and drift is in the opposite direction. And in equilibrium, when you have not added any external circuit, there is no final net current, and so these two are equal in magnitude. Okay? So these two are in equal in magnitude, giving you net current 0. So that is when your p-n junction is just lying on the table, the activities are on, thermal generation of minority carriers are taking place, electron hole pairs are being generated, and recombination is also taking place. There are some nice mechanisms which are different for different kinds of semiconductors. So I will not go into that, but it is happening. And then because of majority carriers, you are having some kind of migration of charges. Then you have minority carriers, they are also contributing another kind of currents, but the net total current is 0. Next, the next task is now connect this p-n junction to some kind of an external circuit. After all this is made to make use of. So let us try to make a simple, very simple kind of circuit, very simple kind of circuit diagram here. So let me connect my PN junction to, here is a metallic contact, remember. Now this is important, we are going to connect it to external world. So this is the metallic contact, and let us take a resistance and then a cell. So when the connections are made in such a manner where the positive side of the cell is connected to the P side and the negative side of the cell is connected to the N side, that means from our battery, from our cell, we are increasing the potential of this P side as compared to the N side. So that is known as forward bias. Forward biasing, it's called biasing, and this PN junction is called forward biased in this particular situation. So suppose the potential difference that we are imposing here through this external circuit is, let's say, VA. This is V applied, but applied doesn't mean this voltage. Applied means what is actually applied on the junction. What will happen? We are increasing the potential of this P side as compared to the N side. So if I take this N side as the reference side, zero potential, call it zero potential. Then before this cell was connected, this was at some potential, already at some potential, you know that. And now we are putting extra potential there. This VA is on top of that. That internal inbuilt potential difference is always there because of the electric field, because of these negative charges here, positive charges here. You have an electric field this way, and this electric field creates a potential difference. We have made all the calculations for that quadratic potential distribution. On top of that, you are raising the potential of this P side with as referred to this N side by this amount VA. And raising the potential means lowering the energy, because U is minus EV. We are talking of electrons, these energies. So these are all electron energies. So in this diagram, what is the effect? The effect is that P side energies are brought down. P side potential has gone up. So P side energies have gone down. So we have to shift this part. We have to shift this part down. That will be the effect. Okay. So let me draw a fresh diagram. So let me draw a fresh diagram of this band. Once again, before the cell was applied, you had a constant Fermi energy, Fermi level for entire material. Then this is P side and this is N side. So here the valence band starts here. This was the valence band. The conduction band was here. And then here on this side, that N side, the conduction band starts here. So let's say the conduction band is here. These are the conduction band energies. All these quantum states correspond to conduction band. Okay, so this is EC here, this is EV here, then this is EC here, and EV will be somewhere here. So the quantum states are here. Then you have this bending. Now what happens, all this energy had to come down. So our new picture will be that this EC has now shifted here. This EC has now shifted here. And I'm writing everything with respect to this N side. So I'm not changing the N side. Okay, it's all relative. The whole thing can be shifted up, shifted down. So it's all relative. So by applying a voltage which is presumably small as compared to this, you have your new EC comes here, your new EV comes here, this EV comes here. And the Fermi level also comes down. Here is the Fermi level, new Fermi level for P side. Alright, so now you have two Fermi levels. For P side you have a shifted lower Fermi level, and for this N side you have different Fermi level. Here this is lower, this is higher. I told you that for one system you should have one Fermi level, but that was for equilibrium. Now we have disturbed that equilibrium by putting this cell, and constantly this cell will keep this potential difference fixed. So by doing this, by forcing this, we will be forcing some current to continuously flow, and therefore that static situation will not be there, and therefore you can have two Fermi levels on the two sides. So this is for N side and this is for P side. Now look at the majority carriers, diffusion of majority carriers. So start from here, N side. The majority carriers are electrons. So you have all those electrons. You have all those electrons here. These electrons are there. Large number of electrons. But as you go up, the number of electrons decreases, and that decrease is also this decrease is also exponential, okay, like that. So earlier which electrons were able to diffuse? Earlier these electrons were able to diffuse. These electrons were able to diffuse, which were having energies more than this energy EC there. But now the EC is shifted here. Now you have quantum states which start from right from here. So now these electrons in this energy range, they can also diffuse to this side. These electrons can also diffuse to this side. Earlier only these were diffusing. Now these are diffusing, on top of this, these are also diffusing. So the diffusion will increase. The diffusion current will increase. And since it's an exponential reduction, the number keeps on getting smaller and smaller exponentially. If you come from top, the number increases, that density increases exponentially. So if you come here, if you come DE distance down, only there is a small change in the number of majority carriers electrons. But the same energy, if you come here or here or here or here, then its exponential increase, and therefore this diffusion will increase many fold. And same will be the story for holes. You can work it out. If this level has gone down, so whatever holes were here in these quantum states, all those holes are now here. The holes now start here. So whatever the density was here just below this valence band, same is the case here. The distance from the Fermi level is same, and therefore it will go further deep. So previously if you had one hole here in the picture, then now you will have many holes here, and all these things are shifted down. So you have extra holes which can diffuse, which will find quantum states here, and therefore the diffusion current I diffusion that increases. So in the absence of cell, you had I diffusion equal to I drift. If you call it I naught, then now the diffusion current is I naught multiplied by some exponential factor, which is in fact like this, EV by KT. Diffusion has increased. This V is this V, VA. What happens to the drift current? What happens to the minority carriers moving through this depletion layer under the effect of this electric field? Look at now the minority carriers. So on P side, the minority carriers are electrons. Okay, so fine. So let me draw on this diagram itself. So the minority carriers, originally your minority carriers start from here. This was the bottom of the conduction band. So these were the minority carriers, and under the electric field they tried to move towards this n side, and successfully they could do that because you had quantum states all over. Now because of the shifting down, what will happen? These electrons now, they are not here, the quantum states are very much there, but the electrons start at the bottom of the conduction band, and that is here. So now those electrons are here. But doesn't matter. If the electric field pushes these electrons in this side, there is no problem. You have all over quantum states here, and therefore they can go in the same fashion. So for drift of minority carriers, this change in the potential barrier or energy barrier or shift in this band, etc., is not going to affect. Similar is the case for the minority carrier here on the n side. On the n side, the minority carriers are holes. So these are the holes here. If they want to come here, no problem whether EV is here or EV is here. These holes can always come to this side. So for small voltages, and generally the voltages on that is small, so it's not as large as this 1.12 EV or so. So generally if this is small, you are only concerned in this area, and here the hole will come independently whether you are here or you are here, EV is here or EV is here. So the message is the drift current is not going to change significantly because of this forward biasing. So what is the net current? The net current is I diffusion and minus I drift, which is I naught times e power EV by KT and minus I naught. So it's like I naught and common e power EV over KT and then minus 1. So this equation is called ideal diode equation. There are several assumptions taken to derive this equation, and that is why it is called ideal diode equation. There are resistances involved, depletion layer offers large resistance, then the carrier concentrations at the edges of the depletion layer, there are some assumptions about those things involved. All those things are there, but it does give you essentially the relation between current in forward bias and the applied voltage, as long as the applied voltage is less than, rather much less than, that built-in potential that is there in the junction. So we will talk more about this equation and how in actual diodes currents go. That will be in next lecture.